Hey everyone, my name is Kanaya Gupta and welcome to my YouTube channel. Today I am going to show you how to solve a staircase dynamic programming problem. Guys, in this problem I will teach you one pattern, and if you know that pattern you can solve multiple problems on dynamic programming which follows that pattern. So before moving ahead, make sure you have subscribed to my YouTube channel and click the bell icon so that you don't miss any update. Let's start. So here is the problem statement, guys. A child is climbing up a staircase with n steps and can hop either one step or two steps at a time. Implement a method to count how many possible ways the child can climb up the stairs. So here we don't have to focus on the complete problem statement. The main thing we have to focus on this. So this problem is based on a child who is trying to climb up a staircase, but this problem statement can be anything, guys. So don't focus on that. That is the story part. So whatever I have highlighted, apart from that, if you ignore all those stuff, you have to come up with a problem statement which is a generic, like you have to reach to the nth step and you can hop either one step or two step at a time, and now you have to tell by how many possible ways you can reach up to the n steps. So here the problem statement is very clear now. Whenever you read the problem statement, it's not necessary that you will get the answer directly. So whenever we have such kind of confusion, we always try to reduce the problem in a smaller part. So let's see if instead of n, if we try for one step and two steps, then see what will be our result. So we are considering currently we have to reach up to a one step. N equals to 1 means the one step, and we can take one step or two step at a time. So if n equals to 1, so there is only a one possible way to reach that stair. So the number of ways to reach on step 1 is 1. In the same way, if n equals to 2, it means we have to reach to the two step or second steps. So the number of ways we can reach up to a second step is either taking one step two times or either taking the two step directly. So we have totally two different ways to reach to a step 2. Guys, I have given a color combination here. So if it's red, it means you have to see the red one, and if it's green, you have to see the green one. So it will be easy for you to trace it. And the good thing is here, you can see by summing up these numbers, you should get the exact number which is equals to n. So let's do this for when n equals to 3. When n equals to 3, there are different ways which we can reach to 3. Either we can take one step at a time, so there is a one way, and we can take two step first and then one, so this is the second way, and the third way is we can take first step and then take two step. So there are three different ways to reach up to step 3. So far we have seen when n equals to 1, it's 1, when n equals to 2, it's 2, and when n equals to 3, there are three ways to reach to the n step. By seeing this, you can maybe think it of, if 1 equals to 1 and when n equals to 2, the answer is 2, so in case of n, the answer will be n. But it may be true for some of the cases, but I will suggest you do not deduce the solution based on some smaller values. You should always try for some bigger value of n. So far we have seen for a smaller value of n, it looks like a same. If n equals to 1, the number of ways will be 1. If n equals to 2, it's 2, and if n equals to 3, the number of ways is 3. Now see for the next step, which is a 4. If n equals to 4, so in that case we can take either one step at a time, and the second combination is take one step two times first and then two steps directly, and the third step is take one step, then two step, then one step, and the fourth one is take two step and then two step, and the fifth one is take two step then one step. So here the total number of ways to reach the step 4 is 5, which is not matching at all. So if you see, previously we can see for 1 it's 1, 2 is 2, and 3 is 3, but here for 4 it's not 4. So that is the reason we should always try to look for the bigger value of n. So let's see the last one, guys. If n equals to 5, here I have already calculated for you. So there are total number of 8 different ways to reach to the 5th step. You can easily trace out with the arrows based on the color. So the first is the red one. So you can see the red arrows like always take a 1 step. Similar to this, I have calculated all the different ways which is possible to reach up to the step 5. So the total number of ways to reach up to the 5th step is 8. Now we have almost tried couple of values. So now fill the table and see what is our results. When n equals to 1, number of ways is 1. When n equals to 2, it's 2. When n equals to 3, it's 3. But when n equals to 4, it's not 4. It's changing it here. So it's 5. And when n equals to 5, it's 8. By seeing this table, what I can see, the each and every number is the sum of the previous two numbers. If you talk about the 8, it's sum of the previous two number 3 and 5. If we talk about the 5 is the sum of the previous two number, which is 2 plus 3. If we talk about the 3 is the sum of the previous two number, which is 1 and 2. So based on that, if I try to calculate the 6 when n equals to 6, the answer should be 13, because it will be the addition of 5 and 8. And the same way for the 7th stair, the answer will be 21. Guys, can you see some pattern over here? If you try to look closely, this is very familiar to us, which is known as Fibonacci series. Can you see that? It's same as the Fibonacci series. Let's see this with the actual Fibonacci series. So if you compare this pattern with the Fibonacci series, you will see Fibonacci has a 2 additional element on the left side because it starts from 0 onwards. But in our problem, the stairs start from the 1 onwards. So for when n equals to 2, the number of ways to reach that stairs is 2. But in case of Fibonacci, when n equals to 2, its Fibonacci number is 1. So basically, our table is n plus 1 Fibonacci. So we are going to take a help from this Fibonacci series or the pattern we know to solve this problem. Let's compare this problem parallelly. So now we have a Fibonacci series on the left, and the right side we have our problem, which is also similar to the Fibonacci. So for the left side for Fibonacci series, and what is the solution or what is the recurrence relation we have? We already know the recurrence relation for this Fibonacci series, which is a well-known program, right? If n is less than 2, return n, otherwise return tn minus 1 plus tn minus 2. But in our case, everything is same, but the base is little bit different. So based on this table, we can come up with this recurrence relation. If n is less than 0, we are going to return 0. If n is equals to 0, we will return 1. Otherwise, we will return tn minus 1 plus tn minus 2. So in this case, why we are having if n is less than 0 equals to 0? But the same condition was not there in the Fibonacci recurrence. Because in Fibonacci recurrence, if you see, if n is less than 0, we are returning n. But if n is greater than equals to 2, then only it will execute the recurrence relation tn minus 1 plus tn minus 2. But in this case, if n is 1, in that case also it will execute this recurrence relation. So once you put n equals to 1, so the equation will become t0 plus t minus 1. So we should know the negative value also. So that is the reason we have put it, if n is less than 0, we will consider it as 0. If n equals to 0, we will return 1. Otherwise, tn equals to tn minus 1 plus tn minus 2. So this is the recurrence relation for the staircase problem. So this is the one way, guys, to deduce the pattern while trying for different values of n and making the series and just try to come up with a pattern. So by doing this, this is the one way to come up with this formula or this recurrence relation. What can be the other approach? Some people, those who are advanced, and once you have done a lot of practice, you can come up with the solution directly by using this approach. We'll see that. Suppose if a child wants to reach up to on top, so there's only two possible ways he can reach up to top. Either he can reach via one step, or either directly he can jump from the second last step. There's no possible way at all. So if you want to reach on the top, you have to jump directly either from the last first step or the last second step, because at most you can jump either one or two, right? So let's take some values, and if you want to reach on 100 steps, so the number of ways to reach up to 100 will be equal to the number of ways to reach up to 99 step plus the number of ways to reach up to 98 step. So when we have 100, so the total number of ways to reach 100 steps is equals to addition of both. So let's consider this for n step. If you want to reach up to n step, so the total number of ways to reach up to n step will be equals to total number of ways to reach up to n minus 1 steps plus total number of ways to reach up to n minus 2 steps. So the total number of ways to reach n step will be equals to this. And the same can be deduced to a recurrence formula, which looks something like this. But here I have mentioned, guys, t0 equals to 1. I'll tell you why. Just now I said if you want to reach up to n step, either you can go directly from n minus 1 or from n minus 2, right? And the total number of steps is equals to the number of ways to reach n minus 2 plus the number of ways to reach n minus 1. What about once you reach there? What about the last these two steps? Because from n minus 2 also you have to take one jump to reach up to n, and from n minus 1 also you have to take one jump to reach up to n. So why we are not counting this step? Because this is also one step, right? So that is the reason we have taken t0 equals to 1. It means whenever you reach to a steps, so now it's a ground level for you, or you can say the 0 step. So for that we are considering t0 equals to 1. Eventually if you think, if you are at ground, there is no steps you are taking. But whenever we are reaching to up to a step, if we are breaking down the problem tn equals to n minus 1 plus tn minus 2, so there is a still constant number of steps which you have to take. So that is the reason we are considering t0 equals to 1. So whenever you reach to that step, we will return t0 equals to 1, because we have to add that one step also. From there you will take one direct step to reach up to n. I hope, guys, this is clear to you. So let's move ahead, guys. So now you know how the recurrence relation came. So this is the dynamic programming, guys, and we know to solve any dynamic programming we will use the fast method. For those who don't know the fast method, I'll suggest please check out my previous video, and the link is mentioned in the description box, and the same you can get it from the top right corner to know the technique to solve any dynamic programming problem. So here I am going to use the same technique, guys. So here F stands for find the recursive solution or recurrence. So this is the recurrence relation for our problem, whatever we have concluded so far, and the same is translated into a recursive code. So you can see, guys, if n is less than 0, we are returning 0. If n equals to 0, we are returning 1. Else we are returning tn minus 1 plus tn minus 2. So this is the recursive solution, and the recursive solution is having a complexity of 2 raised to the power n. Guys, in the last video I have shown you the example of Fibonacci series, and then I got a comment from the people saying that if I can explain how this algorithm is having the time complexity of 2 raised to the power n. So that is the reason here I am addressing that and showing you how the complexity of this solution is 2 raised to the power n. If you use the direct recursive approach, you will end up with an exponential complexity. We'll see how. As we know, the recurrence relation will look something like this: tn equals to tn minus 1 plus tn minus 2. As we all know, we always try to calculate the complexity for the worst case. So in the worst case, what can be here, tn minus 1 will always be greater than tn minus 2, because tn minus 2 will, here we are subtracting the 2, so it will be always lesser than the tn minus 1. But in worst case, tn minus 2 can be equals to tn minus 1. So we are considering in worst case tn minus 2 will be equals to Tn minus 1, and replacing the Tn minus 2 with this. So the reconciliation will be something look like this, right? So once you replace n minus 1, then you will get this, which is, you can see, if 2 raised to power 2 t n minus 2, if the power of 2 is 2, we are subtracting 2. In the same way, if power of 2 is 3, we are subtracting 3. So if you do this type of calculation, and if you go at the end and try to generalize the solution, you will see if 2 raised to power n, then t n minus n, because we don't know any value in this reconciliation apart from the t0, and we know t0 equals to 1. So if you put t0 equals to 1, you can see 2 raised to power n. So this is the complexity, guys, and you can see how I have calculated the complexity. So that is the reason the recursive approach is not suitable for such kind of problem, because it's an exponential complexity and it will take a lot of time to solve your problem. But I hope now it's clear to you how we have come with a complexity. So now the first step is already done, guys. We have find the recursive solution. Now the second step is A. A stands for analyze the solution. So here, if you see or try to analyze the solution, you will see if you wanted to calculate the T4, and the T4 is totally dependent on T3 and T2. In the same way, if you wanted to calculate the T3, it's totally dependent on T2 and T1. So for T4 and T3, we are going to solve T2 again and again. So this is a overlapping problem. In the same way, for T3 and T2, T1 is a overlapping problem because we are going to solve it again and again. As we know, now there's a lot of overlapping problem. So we have to come up with some caching mechanism so that we can save the result and retrieve it in future whenever we need it. We are not going to compute the same thing again and again. So from the first method, S stands for save the result, and this technique is also known as memoization. So if you see, guys, this is the first option. Here we have same recursive solution, but apart from that, we have just added one more condition. If cache is not equals to 0, we are returning from the cache. It means cache is already initialized and we have that computation in our cache. If it's not, then we are computing it and putting it into our cache and returning it. So guys, this is the first approach where we have declared the cache outside. So in this approach, you can declare your cache on a global level and use it inside your program. And you can see, because it's a recursive solution, so we always go from top to down, which is also called as top-down approach. So this is the DP solution, guys, with the top-down approach. As we are using cache over here, so you are not going to compute the same thing again and again. So that is the reason we have a complexity of the solution is On, and the space complexity is also On. So we have reduced that complexity from exponential to polynomial time here by using the DP top-down approach. So this is one alternative, guide, and we have another alternative of this solution. If you don't want to initialize your cache on a global level, so you can pass it as a method argument, which will look something like this. So here it's the same thing, guys, just we are passing cache as a second argument here, and rest of all the things are same. So once we have come up with the solution, you have done with the DP, but still it's not a pure DP solution, because here we are using the top-down approach. The pure DP solution is called when you are having a solution with a bottom-up approach. So let's try to tweak the solution, which is our fourth one, T. T stands for tweak the solution in a bottom-up manner. So this is the tweaked solution, guys, where we have applied the bottom-up solution. So this is the pure DP solution, or called bottom-up approach. Guys, one thing to notice here we are using cache T0 equals to 1, but in case of Fibonacci, it was 0. And I hope you know why we are using in our base case T0 equals to 1. The reason is very simple, guys, because our staircase pattern is not as it is same as the Fibonacci. It's n plus 1 Fibonacci basically. So that is the reason we are using cache 0 equals to 1. So now you know the bottom approach to solve this problem, and the complexity of the solution is same as a top-down approach. The time complexity is On and the space complexity is also On, because we are using extra space here. We are using array of size, but it's not a efficient solution, guys. There is still more room to improvise this. So let's move on to the more efficient solution. To think about the efficient solution, we have to analyze this inputs more, and we can easily see for calculating each and every steps, if you want to calculate the number of ways, that is totally depends on the previous two variables. If you want to calculate the nth step, you need only the previous two details to calculate the next one. So in that case, we are not going to store all those possible combination which we don't need it. We will only going to store the previous two calculation. So if you use that approach, the solution will be look something similar to this. And this kind of solution we have also done in a Fibonacci series in the last lecture. So this is a more efficient solution, guys, because the complexity of this solution is O(n), but space complexity is O(1), because here we are not using any extra space. In all the solution, what we have done so far, either the time complexity was more or either the space complexity. In the DP solution, we have reduced the time complexity, but still space complexity was there. But in this solution, the time complexity is O(n) and there is no space complexity at all. So this is the much more efficient solution, guys, in terms of time and space. So now you know all the steps to solve this problem and with the complexity analysis. Let's do some pattern analysis, guys, now. So now we are going to do the pattern analysis for you. So this is the problem statement on which we are working. We want to reach on an nth step, and we can either hop one step or two steps at a time. And the recurrence relation which we have got was something similar to this. So if you see, guys, because we have an option of either one step or two step, the recurrence relations is also divided into two parts, either n-1 plus the n-2. So in the similar way, if the problem statement is something similar to this, where we can hop either one step, two step or three step, then the recurrence relation will look something similar to this. Because we have added one more step, which is three steps, it will get added to the recurrence. And if you generalize this problem, you can think of this kind of problem statement where we have to reach up to n step, and you can hop at most m step at a time. So the possible ways to reach to that n step will be something similar to this. This is a general formula, guys, so that you can use for any value of m. So if m equals to 4, the recurrence relation will be look something like this. Tn or Fn equals to Tn-1 plus Tn-2 plus Tn-3 plus Tn-4. Guys, this function is given in a form of f, and here I have given in a form of t. So it's totally fine. I mean, you can change it to f or t, but it's just for learning purpose how this series or the recurrence relation is getting expanded based on the value of m. So now you know how you are going to make a recurrence relation for this kind of problem for m steps. So now let's talk about the complexity. If you are using the recursive solution, you will see that the complexity of the solution is O(m) raised to power n, where m is the number of steps which a child can take at most at a time, and n is the total number of steps which he wants to reach. So if you remember, guys, we have done this problem where m equals to 2, because at most it can take either one step or two step. So the complexity which we have analyzed recursive algorithm was 2 raised to power n, because we have only two steps. We can take only two steps at most at a time. If you have m step at most at a time, so it will be O(m) raised to power n. If you see for m equals to 4, then it will be 4 raised to power n. So this is the recursive solution, guys, and this complexity is exponential, which is very huge. And if you try to solve this problem with the help of DP, you will see it can be done in a O(n) time, which is a polynomial approach. Now we are pretty much clear about the complexity and the generic formula. So this is the generic analysis of this staircase pattern, guys. So based on this, you can do any type of problem where the m steps varies. So the key takeaway from this session, guys, if you are climbing up a staircase with n step and can hop at most m steps at a time, then the possible ways you can climb up the n stairs will be equals to this. And the complexity of the solution will be this if you are using the recursive approach. If you are using the DP, then the complexity of your solution will be On. I hope guys now you know the pattern to solve this kind of problem. So in the future, if you get problem which is similar to this, you can apply this pattern to solve dynamic programming problems. If you find this video useful, please like, comment, share and subscribe to my YouTube channel, and do not forget to hit the bell icon so that you don't miss any update. So now let's come to the final part guys. I'm going to show you the demo. So far what are the approaches we have seen, I have implemented and I'll show you in front of you. So this is the first approach guys. So we have used the same code which we have seen in the slides. So this is the first approach where we use the recursive solution, and the complexity of the solution is 2 raised to the power n. And this is the method 2 guys, and approach 1, because here I have used the global cache, and which is declared over here. So this is the one way to solve this problem using top-down approach, and this is the approach 2nd guys. This is another alternative way by passing the cache into the method argument, so that you don't need the global declaration. So this is the approach 2. And this is the approach 3 with the bottom-up approach which we have discussed, and this is the final one which is most efficient approach, because the time complexity is On and the space complexity is O1. So let's run this example. So I'm putting it 5. So for 5, so you can see guys, for 5 the first approach will take this much nanosecond, and the second, the third, and so on. So the minimum one is taken with the last approach, because this is too much efficient. There's no space complexity at all. So this is the more efficient approach guys, and it's taking very less time. If you enjoyed this tutorial guys, please hit the like button. It doesn't take much, because it motivates me to create much more better content for you all. Thanks for watching.